we introduce virtual width networks, VWN, a breakthrough framework that unlocks the benefits of wider representations without the quadratic cost of increasing hidden dimensions. In standard transformers, model width determines representational capacity. Wider layers can capture more complex patterns, but scaling hidden size leads to a quadratic explosion in parameters and compute. This has long been a bottleneck for efficient model scaling. VWN solves this by decoupling representational width from backbone width. Instead of widening the hidden layers, where the cost grows quadratically, we expand the embedding space while keeping the backbone's hidden dimension fixed. This means richer representations are packed into the input tokens, but intermediate computations remain computationally unchanged. How? VWN uses overwidth embeddings. The input token embeddings are widened by a factor of R, say from 4096 to 32,768 dimensions for an 8 times expansion. These wide embeddings are processed through generalized hyperconnections, GHC, a novel mechanism that compresses the wide hidden states back to the original backbone width before attention or feed-forward operations, then expands them again afterward. GHC is a unified formulation that generalizes earlier ideas like hyperconnections and frac connections. It uses lightweight matrices to route information between the wide embedding space and the narrow backbone, enabling flexible, learnable interactions. Crucially, the transformation is done with minimal overhead, just a few extra linear projections per layer. To fully exploit the expanded representation, VWN is paired with multi-token prediction, MTP. While standard models predict only the next token, MTP also supervises predictions for the next 2, 3, or more tokens. This denser supervision trains the model to understand short-range dependencies and compositional structure, exactly where the wider embedding space shines. The result? Massive gains in training efficiency and downstream performance, with no increase in backbone compute. In large-scale experiments on a 3.3B activation MOE model, VWN, with an 8 times virtual width factor, achieves the same next token prediction loss using 2.5 times fewer training tokens. Cuts the next 2 token loss gap by 5 times fewer tokens. And the advantage grows over time. The performance gap widens and convergence speedup increases. This isn't just faster training, it's more effective training. The model learns better representations earlier and maintains a growing edge as training progresses. We also discovered a key insight, a log-linear scaling law between virtual width and loss reduction. Each doubling of the virtual width factor R leads to a consistent, predictable drop in loss, about 0.0069 per doubling. This suggests that virtual width isn't just a hack, it's a new, predictable axis for scaling model efficiency, alongside depth, width, and data. Why does this work? Because the wide embeddings act like a richer memory buffer. The generalized hyperconnections allow the model to learnably access and mix information across layers, creating a soft, dynamic depth context. It's like giving the model a larger, smarter, working memory, without changing its core processing engine. Think of it as a connectivity perspective. In a standard transformer, residual connections allow each layer to see only the previous one. VWN with GHC creates a learned, linear attention-like mechanism over depth, where each layer can access a compressed history of earlier representations, with the ability to forget or retain information via learned routing matrices. This means VWN can support longer effective context windows, not through more parameters, but through smarter information flow. And because the memory budget is fixed, R equals NM, you can tune the trade-off between per-layer fidelity and depth of memory. Higher M means more layers remembered at lower resolution, while lower M gives higher fidelity but fewer remembered layers. We tested this across multiple scales, from 0.4B to 30B models, and found consistent improvements. On smaller models, even a 1.5 times virtual width boost improves training dynamics and downstream accuracy. On larger models, the gains compound. With 8 times expansion, VWN not only accelerates optimization, but also delivers plus 216 points on average accuracy across benchmarks. Importantly, the gains persist and grow. The model doesn't saturate early. It keeps learning from the wider representation, especially on tasks requiring reasoning, retrieval, or long-context modeling, like drop, TriviaQA, and math, where VWN shows the largest improvements. And the cost? Minimals. The additional compute is dominated by normalization and a few linear projections. With smart kernel fusion and recomputation strategies, memory overhead is under 10% of a vanilla transformer layer. This makes VWN practical today, not just on paper. So what's the takeaway? Virtual width networks redefine how we scale models. By expanding the embedding space while keeping the backbone narrow, VWN delivers wider representations at near-constant compute. It's not a trade-off, it's a leverage. We've shown that virtual width scales predictably, synergizes with MTP, and delivers real-world efficiency gains. It's a new dimension for large model scaling, one that's not just promising but already working. And as hardware evolves to better handle wide activations, VWN could unlock even greater potential. This isn't just a technical improvement. It's a shift in how we think about model capacity. The future of efficient scaling isn't just bigger models, it's smarter ones. And VWN is a major step toward that future.